So, welcome to today's lecture. What is happening with the recording? Does it record? I hope so. Yes. Okay. Well, anyway, welcome to today's lecture on CMOS MEMS. It's a hot day. I've left my office at 8:15 and haven't been back there, but I've been baking after my first lecture at 8:30 to 10 in the top floor room. And believe me, this is cool, okay? Oh, and still it's hot. Yeah, so apologies for the delay. I went back to the lab. I get the scripts, and then also I was not warned, but it was remarked that I did not upload the recordings of the lecture last week. Yeah, I transformed the recording into the compact MP4 format, but then I did not upload it into the ILIA. So thanks for the guy, maybe you, who wrote me the email yesterday, and I saw it this morning, and so I uploaded it only this morning. So it may be difficult for you to fulfill any assignments without looking at what I had been teaching last week, especially if you haven't been here. Yeah. So what shall we do? Shall we postpone the discussion of the problems to next week so that everyone has a chance to work on them? Those who have not been here, let's do that on Monday next week, and then I may add a few other problems relating the stuff that we're teaching this week, and then well, it's going to be maybe a discussion week next week. Yeah. Okay. So we have been talking about stress sensor elements, those resistors that make up piezoresistive stress sensors, and on the fact that we have been talking about the fact that they depend on the orientation in the crystalline coordinate system. Yeah? So as a resistor that is highly sensitive to the stress in one in the longitudinal direction, if oriented in one direction of the crystal may not be as sensitive if oriented in an inappropriate direction, and that was translated by transformation rules, allowing to calculate these response values, these pi coefficients, as a function of the orientation of the resistors, and they allow to plot these rosette structures, these stress rosettes, that show that indeed the longitudinal response, the pi longitudinal, is strongest if an N resistor placed on a 001 wafer is oriented along a crystal coordinate direction. This is also crystal coordinate direction, of course, and then there is a minimum in between. And regarding the transversal coefficient, the response of a resistor to stress that is perpendicular to the current direction, that also has an angular dependence, which is maximum along these crystalline coordinate directions, crystal axis of the crystal, and it is even of the opposite sign in the direction at 45 degrees. Now, if you have trouble reading this complicated structure, think of this polar plot to be untangled into a linear plot, because all it shows is pi t as a function of the angle. Now let's see what that translates into. So I'm drawing an axis here with pi t, and then I'm drawing the axis phi, which will go from 0 degree to 2 pi, and this 0 is equal to the 100 direction, and this is again 100, and in between we have minus 100, and then even in between here at 90 degrees we have the direction 010. And so if we look at this curve, what does it say? It starts at 53 point something, times 10 to the minus 11 times 10 to the minus 11 per Pascal. So that is the unit of this pi t, and then it goes, and then let's see where is 0. Let's write some 0 of the vertical scale somewhere here, and then it goes down, crosses 0, and at 45 degrees it has reached a value of probably something like minus, let's say minus 15 or so. So this curve, what it does at 45, this is 45 degrees. Now there's not enough space to write all this. 45, 90, 180, and then 360 in degrees. 45 degrees. And so at 45 degrees, it is negative. And then it goes down to this 45 degree value, and then comes up and is again the same value at 90 degrees. And this it does for every quadrant of this polar plot direction, or it repeats itself 4 times along 360 degrees. So what we see here is that the 0 is crossed several times, and that happens at this angle of maybe, well, 30 degrees. And by 45 degrees, it has become maximally negative. And then by 60 degrees, it's 0 again. This would be this 0. And then at 90 degrees, it's again maximum at 53. I have become aware that, you know, you don't plot so many things in polar plots, and then reading these graphs is not so easy the first time you see them. Once you see this linear plot, then everything becomes quite understandable, because you say, yes, of course, every one of those directions is equivalent, and then it just repeats itself, and what happens between one sector and the next one repeats itself, and that curve is easy to read. In the case of the pi L, fortunately, the situation is easier. So if I now have a second, I'll open some empty pages, I think, here. Should have empty pages still available, not in this program. Cancel. So, yeah, that's so if I plot the pi t curve, so here is pi L, sorry, and then here we have 0, and then this is again the angular axis phi, and now let's go from 0 to just 90 degrees, now from 100 to 010. Then we start at minus 102 times 10 to the minus 11 per Pascal, and then it goes down to which value? The value goes down to minus, I would say, about 25 or so. So let's indicate this on this graph. At 45 degrees, it's down to about 25, and then goes up again to minus 102. Something like this. Okay, and that's it. These curves are actually very simple cosinusoidal curves. Actually, when you do the tensor transformation, calculate the angular derivative that reflects the rotation matrix. There is sinus and cosinus, and then you have some combinations of these sinus and cosinus functions in the transformed, in the phi dependent expression for any of those piezoresistive coefficients, and it can only contain 4th order of these sinus and cosinus combinations, because there are 4 matrices whose elements get multiplied, and that then simplified, shows you that there will be some cosine of 4th order, which can be transformed into a cosine of 2 phi or sine of 2 phi, and that is then squared, and that's what you see here. So, and then there's also an offset term that also adds and that can be positive or negative. That's why we can have some zero crossings in some cases. So that's how these quantities get calculated. And now, of course, we want to also extract those properties from some test structures. Yeah, I gave you some values that are documented by early measurements of Smith, and for N and P doping, relatively low dope samples. But you know, although people always quote these values in their papers, reality for a technical material of another doping may be different. Yeah? And we want to know, and so it is a purpose of material science and MEMS engineering also to extract these properties as relevant for the technologies that we use, so that simulation, numerical simulation, can be used to optimize structures with real parameters, not some general parameters that are more or less appropriate. And so I think I showed you this graph where in the top graph you see the case for N material. So this is N well values in and this N well, if you look at this graph here, yeah, you see these structures, these length. Well, let me zoom in. Yeah, so here are some resistors, test resistors. This is the outline of the resistor. So, and there is a second one here, of course, and those resistors are connected to some metal lines. So here's a transition to metal, and then out goes the metal to a pad, and then at the other side it is also connected to a metal pad. Here you have it. So a current can be sent through, and then there are other metal lines that measure the voltage drop over a piece of that material in a current-free way. Yeah, the voltage instrument that is connected here again, this V instrument between here and here, does not experience any current flow, so that there is no voltage drop from the blue material to the yellow material of the contact, and therefore we don't build in some artificial resistance into the measurement of the voltage drop. This is the purest voltage drop that you can get. It's a 4-point measurement technique, as it is called in the literature. This is very important, because you could also take the resistance measurement from here to here. You also get a value, but then you have a resistance value of blue plus some yellow plus some contact resistance of the two materials, between the two materials, and you get some approximation again. But we would like to do some real material science in such a measurement, and that's why utmost care is taken. And then you see also a pair of structures. So this is a half bridge. So if this structure is now elongated in the horizontal way by a horizontal sigma stress, then this resistor will experience a longitudinal stress, and this resistor will experience a transverse stress. And that is usually how they're built in a real Wheatstone bridge. There are two half bridges, and you get the information out here that you get out from a full bridge, but a full bridge is of course more complicated, and so we can measure some things here. And from the full bridge, you don't get necessarily also the temperature dependence, so it's good to look at half bridges. And then the values that came out here at temperature 10 degrees, well, 30 degrees, let's say something like room temperature, are slightly smaller than what was tabulated by Smith. And the reason is that this N-well structure has a doping that is higher than the structures from Smith. It's not super low doping, and N-well has a doping somewhere between 10 to the 16 and 10 to the 17, and that is no longer very low dope. And as Kanda has shown in this work, actually the piezoresistive coefficients decrease with doping level. And then we have also pi 4,4, which is known from Smith to be much smaller than pi 1,1, the minus 102, so to speak. And then the pi 1,2, which is the so-called 53 times 10 to the minus 11 per Pascal value of two slides ago. And those are reduced a bit. And then here we have P diffusion. So actually, we had to draw it in dashed. There is a second one, which is not explicitly indicated, but it is there. Yeah. So here is the P diffusion. Yeah. How P-doped silicon does not look so much different from N-dope depending on the doping. Now here we saw some contrast. Yeah. In this case, somehow the picture did not yield any contrast, but of course we know what Pascal Gischke, who did these structures and measurements, knew what he designed. And so here is one, and the other is like that, and that is now rotated by 45 degrees, and so it's a P diffusion in a deep N well, and then other measurements can be taken. And here you have an N well again in a P substrate, but rotated by 45 degrees. Yeah? So when you take a wafer and you cut the stripe, yeah, you have the ability to. So let me point this out again on a separate graph. So let's assume I take this wafer. Yeah. I'm making the flat of the wafer quite large so that you see here is the 1,1,0 direction. Yeah? The crystal directions go in these two directions, 1,0,0 and 0,10. Yeah? And now we have these bridges. Now, for instance, the N well we saw in this orientation, and we also see it in this orientation. Yeah. So with its connection, and then so the N well bridges are half bridges are shown for both directions. There are also P well bridges in N well substrate or in N well, and so what can you do? You can now cut a stripe from those wafers, and you can take these stripes and expose them to mechanical loads, for instance, a bending, yeah, in a so-called bending bridge. Then you will have this sigma XX along the 1,1,0 direction, yeah, and here you will have sigma XX along this 45-degree direction, yeah, and then you have to think, what am I actually looking at? And well. That would be something which well is a mixture of a bit of yeah, I mean in the coordinate system, in the crystal coordinate system, a sigma. So if we call this X and this Y, this would be sigma X prime, yeah, and there is no sigma Y prime applied to such a bending structure, and then it is equivalent to a bit of homogeneous expansion, and then a bit of difference of sigma XX prime minus sigma YY prime. And then that is equivalent to a sigma X, sigma XY. So this is kind of equivalent to application of this shear stress. And then you will see a response. So I have to explain this in a bit more detail with also the structures of Hanna. So we will immediately see some test setups that allow us to calculate or to extract these material properties. Then there are other structures that are built on the idea of a field effect transistor. The inversion layer in a field effect transistor, the conduction region between a source and a drain of a field effect transistor is a conducting material. And we can expect this also to react to stresses, conduction property to depend on the mechanical stress applied. And this is indeed the case. And then again, you see here some combinations of half bridges, N-channel FET and NMOS FET, in a substrate doped region in a bulk with this doping here, and of course a p-doped bulk. Here's a p-channel in a n-doped bulk, and again now here the p-doped under 45 degrees, and you can expose those to various loads, and then extract the piezoresistive coefficients. And if I go back to this slide here, everything looks pretty much like one expects, namely pi11 and pi12 are small for the P, and the pi44 is really big, as found by Smith also. And now with the field effect transistors, we obviously see that, first of all, the values are not so simple, and they're not as large either. So in the case of the N-channel device, so this is the N-channel device, N MOSFET. In this case, okay, pi11 looks quite large and negative, and pi12 doesn't look like 50, and pi44 doesn't look like something like close to 0, first of all. And second, it depends also on the source, on the biasing of the device. So how strongly is the bulk biased with respect to the source? So there is the source drain voltage, there is the gate voltage, and there's the body voltage or bulk voltage. And now the biasing of the bulk influences how strongly inverted the inversion layer is, and that obviously has a strong influence on the piezoresistive coefficient. So in order to do a design of a stress sensor, a real stress sensor based on field effect transistor, one has a few more parameters to respect. And so an intricate know-how or knowledge of the response of these sensors is important. But when you have that knowledge, it's easy to design a good sensor. What about the P MOSFET structures? Well, here pi44 is large as expected. Pi11 is small, but pi12 is also quite large. So, and the biasing dependence is a bit smaller. So we wrote a paper that was published in the Transactions on Electron Devices describing this in detail, so that people have a basis for the simulation of such sensors. So now, after all this theory, let's look at some real devices. And then once we have seen the real devices, we can look at how they are characterized in some setups. So what you see here is our field effect transistor devices, so FETs, piezo FETs. Piezo FET, a FET consists of a region that is conducting, and in the left cases, this region is all you see here in the center. So this is the region that is spanned by the gate. Now there is a gate on top, so in cross section, you have the silicon component, you have your source drain, you have here the gate oxide, and then let me draw the gate in yellow on top of everything. So here is S, source and drain. So, and of course, I mean, all those contacts need to be biased. There are metal contacts that contact them, and then there are insulating layers, as in every CMOS technology, and this is now very schematic. Here is also a contact. It's of course to the back between the layer sandwiches of the dielectrics. And the yellowish structure that you see here spans this entire region here. So this is a gate, and the gate is contacted at these locations. So these are the gate contacts at all. No, sorry, wrong. I need to draw that again. The gate is contacted here on those sides. So these are the gate contacts. So it's symmetrically contacted. And then, of course, there need to be the source drain regions. So what is the source drain? This is the source here, and this is the drain. So where is the source here? Well, in a stress sensor of the Wheatstone bridge type, we have 4 sources and drains. So here they are. And they are connected by their own metal lines in this direction. So what you can do now is to send a current through the device, for instance, along this dashed line from one contact under the gate in this inversion layer, creeping along the oxide silicon interface as an inversion layer. It spreads over this whole device and then is collected again at the drain opposite. And of course, it creeps there because there is a potential landscape, a voltage drop landscape from one contact to the other. There are different voltages. And then these equipotential lines span the structure, in some geometry. And if there is no mechanical stress, then there will be an equipotential line between these perpendicular contacts. Now this looks like a Hall sensor, and sure enough, it would act as a Hall sensor if a magnetic field is exposed to a magnetic field, but it's also a stress sensor. And this and the voltage difference between this contact and this contact is indicated in your graph as VPH, V pseudo Hall. It's like a Hall sensor, pseudo. Means kind of Hall, but it means a mechanical stress, and we call it also the shear piezoresistance, the shear piezoresistive response that appears here as a voltage. And the structure here is designed as an NMOS structure, which means that the inversion layer is N, which means that the substrate, the bulk underneath, the well underneath must be a P well. Yeah, and then you have the same structure also realized as a PMOS device. So there is an N well, there are 4 sources and drains that you see here now in these 4 corners, and the gate is now, the whole structure is now rotated by 45 degrees. And it makes sense. This makes absolutely sense. And in order to see that this makes sense, you see, when I look at this structure here, you think, okay, let me expose it to some stress of this form. We call this X prime. Sigma X prime X prime, sigma X prime X prime, and then I can also do some sigma Y prime in the opposite direction to make this consistent with the earlier slides of this chapter. So pulling apart horizontally and squeezing it from top to bottom. Would that cause any piezoresistive response? Obviously not, because the 2 contacts, they are still symmetrical with respect to that application of stresses. Pulling along makes, and I like to use this geometrical picture, makes the device longer in this direction, but what was vertical in the middle still is vertical in the middle. And so there is no geometrical deformation apart this elongation. So definitely this response would not, does not cause any pseudo Hall voltage to appear. But if I did it in this direction, like this, then sure enough, it would. This device here will react to sigma XX or sigma YY, a difference of those two. And that is equivalent to a sigma X prime Y prime. So if this structure is exposed to a shear stress, it will respond. But that shear stress in this prime coordinate system is equivalent to a difference of normal stresses in the crystal coordinate system. And the piezoresistive coefficients that are associated with these normal stresses are maximum for n carriers. So this structure is oriented as it should to exploit piezoresistive coefficients maximally. If it was a diffuse structure, it would definitely be good. Since it is a field effect transistor structure, well, we exploit still a large span between pi11 and pi12 because it's the difference of pi11 minus pi12 that plays a role. And the PMOS structure can be oriented in this direction. Now we can expose it to this sigma XX prime stress that pulls and pushes like this and or pushes like this, and it will yield a response because you can imagine that this structure now becomes longer along its edges, and so the current resistance along this direction is larger than along that direction, and therefore this potential will no longer be right in the middle between the potential of those two contacts, the source and drain contacts. And vice versa, this one will be shifted in the other direction. So there will be a pseudo-Hall voltage difference. And if you don't believe this to happen in these devices without hole, let's look at devices that have a hole. In this structure, what you see is a structure that consists of kind of 4 resistors. So we have a first resist. I can draw that in yellow. It looks like there is a first resistor in this between this source and this drain contact or this middle contact, and then there is a second resistor between this middle contact and the drain contact at the other side, and vice versa at the bottom. And of course, this structure here reacts under shear stress, or it's easy to see that it will react to this sigma YY, sigma XX difference, because that resistor gets pulled in the longitudinal direction and squeezed in the perpendicular one, whereas this gets squeezed in the longitudinal direction and pulled in the perpendicular one. So that's ideal to obtain a shift of this potential between half of what these potentials are. So a shift from the stress-free voltage. And in the bottom, it's just reversed. So this will just respond the other way. So we will have quite obviously a difference in voltage between these two contacts under the sigma YY, sigma XX difference, or equivalent under a shear stress in the coordinate system aligned with this picture. And vice versa down here, it's easy to see that if this structure gets pulled in this direction by some X prime, of course, it will be elongated here and here, and those resistors will be elongated perpendicularly, and that will cause a different response of these resistive segments, and therefore a voltage difference between these diagonal contacts here in this case. And the current is sent through the structure around. Let me remove those last arrows. So the current now flows, of course, like this and like that around the corners from the source to the drain contact. So this is these are some structures that were designed again by Pascal Gischke and that have been implemented in many stress sensor systems. And so how to calibrate those sensors, that is done on a so-called 4-point bending bridge. That's one instrument, and then on a torsional bridge that were constructed and exploited in my lab. And so what does one do? One takes indeed a stripe of the material, cuts it from the wafer, and then let's say there is a chip, and then it has its stress sensors, which are connected to, well, some instrumentation. And then this bending bridge is bent in a very well-controlled fashion between some fixed supports that are out here, the outer supports, and some inner supports that just move up and at some point contact this stripe of silicon and then move higher up to give it its bend. And the nice feature about this 4-point bending idea is that in the middle, in the inner, between the inner supports, the curvature is constant. So the stress is independent of the location. So if your chip is slightly more to the left or slightly more to the right, you don't have to worry about that. It always experiences the same stress. And that means that the stress sensors, wherever they are, experience the same stress. And so for a characterization method, that is good not to have additional parameters to control. If you did a simple experiment, quick and dirty, as people like to do also, that's also good to get some first idea of some things. You would just hold the stripe, clamp the stripe on one end, and then load it on one side, push it down, you also get a curvature, but that curvature depends on the location. It's strongest at the support, and it's weakest where you apply your finger. If you don't apply a momentum, a torque, then that curvature just dies to zero. It vanishes at the load application site, and that makes it independent here. Just like the curvature that you have in these outer segments goes from the value that you have inside down to zero. Actually, here there is no more curvature, and here there's no more curvature. If you wanted to draw this object mathematically correctly. So here it's a circle of a segment of a circle. And that allows now to apply, of course, sigma x prime stresses in this direction by just bending, because the top surface has to expand to curve around this larger radius of curvature, whereas below it would be compressive, and in the half of the beam there is a neutral plane that does not experience any stress at all. But above that neutral plane, of course, the material is stretched, and that is what we exploit to apply a very well-controlled uni-axial longitudinal stress to sensors. So, and then there is this other instrument that is called the torsional bridge that is ideal to apply shear stress. So if you take a bar with circular cross section and you twist it, you can easily see that segments get twisted, and if you had a square drawn on the surface, it would deform into some rhomboidal shape. That is the effect of a shear stress. So this is the material to load a material. This is a method to load a material with pure shear stress on the surface. And that is what is happening also here. When you take such a stripe and then just rotate it mathematically correctly around its central axis, then the surface will experience a pure shear stress. That's a delicate, I mean, both experiments have their delicate aspects, because you would like to apply a pure stress of a kind. So you have to avoid that the 4-point bending bridge at the same time twists the structure a little bit. That would be easy to twist if those inner supports are not fully parallel to each other, slightly twisted, yeah, you load the structure and it rests on both supports and then it gets twisted while being bent. Yeah? So calibration of these structures and flattening those inner supports is an important process of making sure that the measurement is correct. And then in the case of the torsional bridge, try to take a bar and only to twist it around its axis without bending it. Not so easy. Yeah. So there needs to be a little bit of engineering know-how. Now, mechanical engineers have made all those inventions how to reduce the numbers of degrees of freedom when applying loads. And so in the 4-point bending bridge, that is quite well done with some alignment gauges and some tricks to make these things flat. And so my technician knows how to do that. And there are these alignment screws that can be used to adjust the structure. And then, well, it's kind of difficult to see. Well, here you have to imagine a silicon stripe, which is placed underneath these large jaws that have these rods underneath, against which the silicon stripe is pushed by this elevator stage that has two inner rods that pushes the silicon stripe upward. And because you would like to make some electrical measurements at the same time, the silicon stripe has to be electrically contacted to some PCB that you see here. PCB has a hole. It has its gold, electroplated gold contacts, and then some bonding, wire bonding is done to connect the sensor being calibrated, or the structure being calibrated to these contacts, and then to the external instrumentation that sits out there. And again, that took some brain work by people and experimental work, refinement, to figure out how to do that, because of course you do not want to the stripe to be loaded by this PCB. It must not be in contact. It can be electrically contacted by these supremely delicate bond wires that will not exert any significant force on the stripe, but a mechanical contact with the green PCB would be highly disturbing. And so for the mounting, the PCB and the stripe are somehow intricately pressed against each other by these screws. There is a little structure under the stripe that holds the stripe, and you can mount it, and then you loosen those screws and somehow elevate the green part a bit away. While this is being done, the bond wires deform a bit, but thanks to correct bonding, this is feasible. And then you have a freely moving silicon stripe underneath. In the case of the torsional bridge, you see here a stripe. Now this is nicely visible, being clamped at both ends, and then again connected to that same PCB and bonded to that PCB, and now this top part is fixed and the lower part can be rotated around the axis. And in case this was not perfectly aligned and perfectly in the middle and so on, for this case, there is this very elaborate hinging, kardanische Aufhängung, it is called in German, that allows all the other degrees of freedom to be released, except the torsional degree of freedom. So there is an axis that allows this component to rotate. Where is it? So there is an axis. Let's make this in another color. So here is an axis that can rotate, where this structure can rotate back and forth. And of course, it can also move up and downward here, slide up and downward. So this can also move in this direction. And Yeah, that's pretty much what you need to remove other degrees of freedom. Same structure is also implemented up here. So this is released except for the rotational degree of freedom. Yeah. Okay, and then you see here some results. For instance, a stress sensor, an NMOS stress sensor under the shear stress. Yeah. So this is the upper left sensor here. NMOS, either this one or this one, actually both. With hole and then standard, the hole-free one. And they react to this shear stress, sigma x prime y prime, as promised. And actually the one with the hole does more so than that without a hole. So it's a better stress sensor. The Wheatstone bridge is the best stress sensor. There's no doubt about that. And the sensitivity is indicated here with 300 or so microvolts per applied volt per megapascal of stress, and that's a fairly good number. Yeah. And then here those NMOS sensors with hole were characterized, by the bunch to show some statistical variations among the samples, and actually it's amazing to see how stable the sensitivity of these field effect transistors are. I mean, CMOS technology is about producing identical transistors. And so they seem to be identical also from the point of view of piezoresistive response. What is not so zero or same among the sensor is the offset. There are many parallel curves in here. They all have the same slope, but their vertical position is slightly different. It varies by roughly a millivolt. So a few hundred microvolts, let's say a millivolt. And that is because, well, those transistors are not placed and those contacts, those source drain contacts are not placed exactly symmetrically. As we have seen already with the Hall sensors, their small shifts cause offsets. And that's what you see here. And if 1 volt is applied and you have one millivolt of offset shift, it means that it's basically precise to 1 part in 1,000 with respect to the overall dimension. If that dimension is 10 micrometer and you have 1,000th of 10 micrometer, it means that the contact is displaced by 10 nanometers. So it's fairly precise. This is nothing that worried us because it just shows the natural limits of the technology. And here you have the corresponding results for the PMOS sensors on the 4-point bending bridge. So PMOS, these are these sensors down here. To what are they sensitive? Well, to these longitudinal stresses. And those longitudinal stresses can be applied by the bending bridge. So let's expose them by the bending bridge, which means moving up the lower stage. And at some point, we have contact. Up to this point, the sensor is just stable. It experiences no mechanical constraint, so it has the same response. Let's call that 0, shift it to 0. And then at the point of contact, the slope changes because then the beam starts getting deformed. The higher the shift is, the higher the stress and the higher the output voltage of this 4-point sensor. And again, we have some sensitivities that are very, very comforting. And again, the one with the hole has the higher sensitivity. That's a geometrical effect. And again, there is an offset that is actually even larger here. 2 millivolts, plus minus 2 millivolts, around almost 0. But again, the sensitivity is highly constant. And the fact that this number, it's not identical. So that these numbers are similar is due to the piezoresistive coefficient that somehow add up to something similar. This is an example of the smallest shear stress sensor, or stress sensor, that piezo FET that was ever realized in my group. This is by Michael Dölle, one of my earlier PhD students, and he just went to the limit of the CMOS technology, which then was a 0.6 micrometer CMOS technology. You see the 4 source drain contacts. So here, 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 and here. And in between, there is again the gate. Let me draw it kind of with this shape. And the gate is contacted up here to its gate line, whereas the 4 contact lines just reach away here. And then there is also another contact, this ring contact, which contacts the well in which this transistor is built. So what is that? That's a P-channel piezo FET, so there must be an N-well underneath, and that N-well has a highly doped N-well diffusion, and that N-well diffusion is contacted by this line here. So the distance, the smallest dimension here, the distance between pairs of source and drain contacts here, or contact pairs, is 0.6 micrometer. That's what the company promises to produce. Of course, nowadays you could go smaller if you wanted. That's not sensational, but I mean, the lines are so wide that it doesn't almost make sense to make the distance smaller. You gain nothing by making the sensor smaller. But anyway, this was the smallest one that we realized. Now, so far we have talked about in-plane stresses. So longitudinal stresses in the plane of a chip, or shear stress, compressive, tensile stresses. What about stresses that are out of the plane? Can one measure those too? We have seen an example of a Hall sensor that can measure the unexpected direction of the Hall field, namely of the magnetic field, namely in the plane, instead of perpendicular, as is usually done, by turning the sensor in the vertical way. And this can also be done with stress sensors. So you have basically 4 contacts. So let me just talk about this, and this equal this contact. There is a contact line going around. So current can be sent in here and flow to that outer contact through these 2 ways. And it turns out that if you make that current, so in the inner section, it looks like the current goes simply down, downward. The current here doesn't know so much about these outer contacts where it has to go ultimately. But anyway, in this area, you can now add these sense contacts between which the pseudo Hall voltage is measured. And which stress will that measure? The shear stress, the vertical shear stress. I mean, it's clear that a vertical shear stress, again, taking as a simplification or a help for the thinking, a shear stress will geometrically kind of deform the structure into something no longer symmetrical with respect to the vertical axis. And so the current flow will necessarily become asymmetric also. Left and right is no longer the same. And therefore you can expect a voltage to appear between this contact and this contact. In reality, of course, it's the band structure. It's not the geometry that makes the effect, but mentally it helps. So this is indeed the case. So if we have here an X, Y, and Z coordinate system, for instance, this plane that we see here is the XY plane, XZ plane, and the stress sigma, no, not X, I thought something and I said something else. YZ is the YZ plane, and the YZ shear stress is what causes a voltage difference here, a delta V pseudo-Hall or V out YZ, as it is called here, an output voltage for the YZ in the YZ plane proportional to the shear stress in that YZ plane. Proportional also to the input voltage between the contacts, and then the relevant shear stress piezoresistive coefficient, which is the coefficient pi44 in that plane. So you may have to calculate the pi44 in that plane, depending on the orientation of the structure in the crystal coordinates. It may be calculated, and since this is a p epitaxial layer, it may be that actually, then the pi44 is actually large. If this is a 100 plane. And then there is a geometrical factor, geometry factor lambda, which takes into account that the fact that this is not a perfect Wheatstone bridge, it's anything except a Wheatstone bridge. It acts like a electrical Wheatstone bridge, but it doesn't look like a Wheatstone bridge, and that makes here this geometry factor that is much smaller than 1, of course. And then Benjamin Lemke, who invented that sensor, designed it, and characterized it, also implemented the same in the perpendicular direction to measure the shear stress in the XZ plane. So the second component of the shear stress. And this produces then an output voltage between this contact, let me point this out in orange, and another contact here in the front on that X line, and the surrounding contact, of course, goes also around the whole thing. So this encloses the structure like this. It's a circular square surrounding contact. And viewed from the top, you see the central contact, you see this surrounding contact. Actually, here is a surrounding contact. And then here are these 4. Actually, the surrounding contact is this one. And then you see these 4 other contacts that allow to measure the pseudo-Hall voltages caused by these 2 components of the shear out of plane shear stress. So let's look at the stress tensor. We have sigma xx, sigma yy, sigma zz, sigma xy, which is also standing here, sigma xz, and sigma yz, sigma yz, and sigma xz, symmetrical stress tensor. Now, what we learned how to measure is this in-plane shear stresses. So they are kind of done. They can be done by in-plane piezoresistive bridges. Then what we also can do actually is measure the difference of those, sigma xx minus sigma yy. That's also okay. So of those 3 components, we can actually measure 2 combinations, one pure and one in combination. Then we have learned how to measure out of plane shear stress, namely, let me put that in another color, sigma xz and sigma x yz. So those are also done. And now, of course, those are also the same. So we can measure those. And now the final question is, can we also measure something about the normal stress itself? and we measure the stress, the normal stress in the Z direction applying to such a chip. And that's a more difficult problem. Just as it is difficult to measure, it's actually impossible to measure these stresses sigma XX and sigma YY to separate those. With piezoresistive sensors, you cannot separate those. And I mean, we have done enough thinking, and there are reasons to believe, not only to believe, to know that actually you can't separate them. Sigma XY is also a combination of a longitudinal stress and a compressive perpendicular stress. It's also a combination of two longitudinal stresses. So, and those, that's just a shear stress in under 45 degrees. We can measure shear stress with these sensors and in these Wheatstone bridges. And if you would like to measure the stresses independently, well, I guess you are in trouble, unfortunately. So how to measure the vertical stress? Benjamin again thought about that, and he said, okay, let me just make a resistive sensor. So a central contact and then a surrounding contact ring, and I'm sending in current here and getting it out at the peripheral contact. And then I can just measure the voltage drop between these two contacts. And that's a purely resistive measurement. So there's a vertical resistance, there's another vertical resistance out there, and there is a fraction of horizontal resistance also merged into the structure. And the of course, the vertical sensors will respond to the vertical stress by the longitudinal piezoresistive effect. Now, if you push, maybe there will be also in-plane stresses, because the material wants to expand and it can't. So there may be by the Poisson's ratio, by the suppression of the perpendicular expansion, there may be also perpendicular stresses, which will also load onto that. But let's assume there is only the out-of-plane stress. But the out-of-plane stress will also work on that horizontal resistor, but through the transverse piezoresistive coefficient. And then if we have isotropic in-plane stresses, they will work on those resistors also, here perpendicularly, and here partly longitudinally, partly perpendicularly. So if you fudge this all up and calculate the response of this sensor under mechanical stress, well, you have a resistance composed of 3 resistors, and the change of the resistance, delta R, under an arbitrary situation with sigma ZZ and sigma XX plus sigma YY, can then be extracted as this formula that you see here that has piezoresistive coefficients and a geometry factor gamma that somehow says how large the vertical component is in comparison with the complete resistance of the structure. So, that's the percentage of verticality in this resistive structure. So this is what you get out. And here you see the problem of the purely resistive sensors. Purely resistive sensors like this one also react to temperature. It has a temperature coefficient. The linear coefficient of temperature of resistance is called alpha here. And if the temperature changes, you get also a relative resistance change. And then you don't know, was it temperature or was it mechanical stress? That's why we hook up the structures into Wheatstone bridges so that this alpha delta T, which is the same in all the resistances, gets canceled. But because of that cancellation, we lose one piece of information. then we only measure sigma xx minus sigma yy and no longer the individual components. Like we measure here one stress information in a pure way. It's kind of a fudged up combination of sigma xx, sigma yy, and sigma zz, but it's one clear piece of information. And so as long as you cannot compensate the temperature, you may extract stresses, but if the temperature is not constant, which it never is, then you lose a piece of information. So here, this was the state of the sensor of Benjamin Lemke, and of course he had a lot of trouble to characterize it, to get this mechanical stress response out, because the temperature could not be held constant enough. And those resistors vary a lot with temperature. These are N-well resistors, so pretty low doped. And so then he said, okay, now what I will do, I will operate that sensor under two modes. What I can do, I can shift the potential of these inner contacts with respect to the P-well that causes this verticality and the surrounding P substrate. I can hook them up and then bias them with respect to the inner conduction region. And of course, that has an effect on the width of the depletion layer between P and N. Varying this VB will make the depletion layer out here larger or smaller, depending on whether you're going more in reverse or more in forward direction, and the same here. So by varying VB, you can vary the geometry of the sensor. And that means that you can, let's say, make this vertical channel narrower, and this vertical channel narrower also, or you can make this horizontal part narrower. And depending on how you design the structure, the ratio of vertical to horizontal, this gamma factor can be modulated as a function of the biasing. That's what the purpose of the whole exercise is. Somehow modify RH differently from the modification of RV, and then your gamma is different. And then you have 2 delta R over R zeros with 2 different gamma values. And if you now take the difference of those two and assume that the alpha is the same, okay, big assumption, then you can eliminate the alpha delta T term by subtracting, and then it's amazing, then you extract a piece of information of that sensor that is a stress information that is temperature compensated for the resistive part at least, and it looks fairly decent. So here you have pi11 minus pi12, that's usually a large value, and then you have gamma 1 minus gamma 2. You have to bias it so that this structure, this difference is large, and then you have this measured difference of relative resistance changes. And so that was as close as we could get to measuring sigma ZZ. No other way to measure sigma ZZ in a pure way is known to us. So let me just summarize the performance of these sensors. So first of all, they can be used to measure stresses up to several hundred megapascal. And in mechanical sensors, this is the level of stresses that you get. They are highly sensitive with several hundred microvolts per volt per megapascal of sensitivity. They vary little among samples. They allow comfortable sub-megapascal measurements. So with hundreds of microvolts per megapascal, you can also go into the 100 kilopascal stresses and still measure tens or microvolt per input volt, and that's measurable. They are temperature compensated. Those Wheatstone bridges are temperature compensated, and that's with respect to the resistive part. That can vary as a function of temperature, and the temperature effect is compensated when you drive them at a given fixed voltage. Now, the circuit designer have a worry because they would like to apply a voltage that is temperature independent. And those current sources have their own reasons for being temperature dependent. And to do a design that is temperature insensitive is an art. That's the art of analog circuit design. Then they have offsets of 100 microvolts to millivolts that correspond therefore to several megapascal. But those offsets can be compensated. If you know them, then you can just subtract them and then you have your zero. Individual offset calibration is necessary, however. And then what about noise? Well, there's a noise floor of about 10 nanovolt per square root hertz, or 18 for these NMOS and PMOS over a wide range, where the noise is white noise. But field effect transistors have also at low frequencies a 1 over F noise part, and that starts about at 400 or 1000 hertz for the NMOS and PMOS. So it's from the system point of view, it's better to operate those devices at higher frequency, to do some chopping at high frequency, and then you got rid of the low noise part. So there are switched capacitor and other chopper techniques that the circuit designers apply to make these measurements. And the nice thing about these structures is that they can be small. The field effect, the piezo FETs can be quite small, as I showed with one example. And so they can be arranged into arrays quite easily, much more easily than these bulky diffused structures. And then they have a big advantage. So over those resistive devices here, the piezo FETs have the advantage of this built-in switch, the gate voltage. If you have an array and you would like to read out one device, you switch the gate voltage of that one device to inversion, and then the current can flow, you can do your measurement, and all the other ones are highly resistive because the gate voltage makes this device to operate in well below the threshold, and therefore no current flows. So this is a fantastic advantage which you don't have with diffused sensors, where you apply a voltage and the current immediately flows. There is no additional switch built in. So and this has enabled some applications that I would like to show you now. So for instance, this array, that is again due to Michael Dölle. He now works for Zülke in Munich in a responsible position. And you see here an array of 32 by 32 stress sensors. Each one of these little pixels is a sensor with 4 contacts and a gate on top. And then, of course, there needs to be some multiplexing structure, and then some digitization structure, and so this was all built in here based on circuit blocks that were available with the company. This was fabricated at X-FAB also, and so this was Michael's design with the addressing logic and then the internal logic, and then so for instance what he could demonstrate is that this really allows to identify the location of contact. So you push on one location. You can imagine that a force exerted at one location in the vertical direction, so F, let's make this another color. Let's say this is Fz. This pushes onto the surface, and by pushing onto the surface, it will compress the material in the vertical direction. The material wants to expand, it can't, so there will be a radial stress sigma RR I say radial. In any direction, the material is compressed. So here it is sigma xx, here it is sigma yy, and it's the same. And the farther away you are from the contact, the smaller this compression will be. Close to the point of contact, it will be largest. And so this in this case, here we have a coordinate system. So this compression is called sigma yy. Here it is called sigma xx. So at this location, if I go at this location and blow it up, make it a bit larger, I have this sigma xx component that kind of I drew now a longitudinal and an expansive stress. I should have drawn something compressive with the arrow tips pointing towards the center. They're compressive. The material is compressed. So let me just correct that here, so that at least you have it correct here. So. So the material, piece of material here in the center, is compressed. So because it is compressed, it would like to expand, but it can't. So it will be certainly also compressed a little bit in this direction. So there will be a little sigma yy, which would be called sigma tangential in the tangential direction. Let's call it sigma yy here. And so there is a stress difference of compression in the x direction and in the y direction. And that difference, sigma xx minus sigma yy, has a certain sign, and it is negative. Sigma xx is negative, sigma yy is not as negative, so we have a negative value. If we look on the left, same value, negative. If we look at the top, sigma xx minus sigma yy, has now the opposite sign, because the role of x is taken over by yy. This is now the component that has the large direction here. Like this pair of arrows, we have this pair of arrows here, and then we have the smaller perpendicular compression, which is now the tangential direction here, which is the x direction. So x and y have switched order, and therefore the sign has changed, and that is exactly what is measured. So we have these positive sensor signals in this sector with maximum around this horizontal line, maximally negative, and then in this sector it is maximally positive along this line. And when you look at the values as a function of angle, you would just see a cosine square function, or actually a cosine is of 2 phi, going up and down from plus to minus to plus to minus. And so this stress map was constructed from the measurement from the output voltages of these stress sensors, these 32 by 32 stress sensors. So you can do stress mapping. That's what the demonstration was. And stress mapping doesn't need any such dense arrays necessarily. Here's a sensor chip. It was done by Pascal Gischke again. Gischke is now with Bosch Sensortech, and he did a system that had 32 stress sensors, namely 10 NMOS piezo FETs for measuring sigma xy. So now the coordinate system xy is this coordinate system xy. So NMOS for measuring shear stress, 14 p-type or p-channel piezo FETs for measuring sigma xx minus sigma yy. And then it also had, shown in yellow here, these 8 vertical shear stress sensors with the 2 with the direction sigma x z and sigma y z for the measured shear stress. And those sensors are all hooked up to some digital, again, multiplexing circuitry and some analog circuitry, allowing to amplify those structures. And those amplifiers were nothing designed by them, but taken over from the design library of the CMOS fab, the foundry, and then digitized to come out of the system as a digital signal in the format of an I2C bus signal. And so what can that do? It can measure the stresses, these stresses indicated here at various locations on the chip surface. And if that chip is now embedded in a system where it is exposed to all kinds of mechanical loads, those different mechanical loads will produce different signatures in this distribution of sensors. And by measuring the response of those sensors, one will be able to tell what the combination of loads is. So that's the purpose of this thing. And so if you imagine this chip now being embedded in a package and being exposed to forces, to moments, the purpose of this built-in chip is now to extract those forces, moments that are applied to the package. And actually this was applied in this so-called smart bracket system, where you have these mock-up teeth with a sensor on its base, now embedded in between, equipped with a bracket slot, as it is called, and then ligated to a wire. And of course, such a wire exerts now which color shall I take? Exerts a force in this direction, but it may also exert a moment around a perpendicular axis, and actually it will also exert a force component in this direction. So we may have Fx, we may have Fy, we may have Fz, but we also have Mx, My, and Mz being all applied simultaneously to that tooth. And it's this combination of forces and moments, torque components, that exerted on the tooth that make the tooth shift progressively in the jaw, because the tooth is rooted with its rule in this alveolar bone cavity, separated by some softer tissue, and under pressure that tissue causes biomechanical reactions, so that bone is digested or removed or dissolved on one side and built on the other side. And so if a force is applied to a tooth, it may just shift to fill a hole between two teeth. And after a few months, this hole may be gone. But it is important to measure these forces, because if you now only act with this horizontal force component, let me put that in black here, you can see the contrast so well. This horizontal force component, Fx, the tooth may not just shift, it will just rotate into that cavity. Then you have to rotate the tooth, which may not be good for biting. So at the same time, while pulling on the tooth, you need also to rotate it counterclockwise, to make sure that the root that is up here moves horizontally and not just rotates around its center of gravity. So this was the purpose of this project, and with Professor Lapatki from University of Ulm. And you see here that actually those smart brackets are hooked up with some cables to the external instrumentation. That is something which you cannot apply, of course, to a patient. This was only for these clinical studies that were done here with particular loop segments, so that the orthodontist, the orthodontist researcher like Lapatki can optimize application techniques. But if this is to be applied to a patient, of course, it needs to be equipped with a non-contacting transmission of energy and information and data, and that requires a method called telemetry, And this spring, actually, one PhD student, Julian Hafner, passed his PhD thesis on this integrated system equipped with telemetry functionality so that you can approach the smart bracket with a loop, activate it, get the measurements out, and then move to the next one, activate it, get the measurements out, and then you have a picture of the whole dentition of what the force and torque components are. And so here you see an early test setup that was built to characterize the mechanical situation of entire dentitions. And this is basically a cross section of the system where you see, well, the chip down here. Let's make this yellow here. So you see the chip embedded here between a base and then the slot, which is again ligated to a wire. And that chip bears those sensors that allow to extract the different components of the forces and the torque that are applied, because each of those components produces a different response. And I will stop with this experimental graph that was a calibration result that showed that actually what was extracted, or what was concluded to be the force components Fy, Fz, Fx, is indeed what has been applied by some measurement setup that we conceived. But it also shows that actually some components are not so well measured. In that case, namely the component Fz. The pulling on the bracket here in this perpendicular direction. This Fz was not yet satisfactory. Then in the meantime, this problem has been solved by some mechanical design that have nothing to do with the chip, but with the way it is embedded. It's more the packaging that made this possible. And the moment components could also be measured quite beautifully, even if they are combined. Sometimes they're separate, sometimes they're combined, and you get a fairly good response out of that. So with that, I would like to stop, and I will continue with this high pressure sensor next time. That is tomorrow at 2 o'clock. So thanks for being here, and see you next Tuesday or tomorrow. Bye-bye.